Hello and welcome to New Uses for Old Circuits, a new series that I'm doing here on YouTube to explore linear and nonlinear dynamics in the modular synthesizer. I wanted to start off by thanking everyone who checked out my series on cybernetics from a few years ago. The response was really nice, especially for a kind of thrown together series, and I really enjoyed hearing how much people got from it. When I started the series, I had a pretty clear idea of what I wanted to talk about and what I wanted to explore. And I really did not want it to creep and become a sort of unending slop of YouTube content. At the time I made this series in 2021, kind of amusingly, as I was talking about things like neural networks, artificial intelligence, and all of that, things like LLMs were really starting to take over, and AI slop was starting to break containment and sort of seep into every aspect of our lives. This series is a little more open-ended in its conception than the previous one, but I promise I won't be just churning out content for the sake of it. I like to make sure that every video I post has a reason and that I feel like I have something to say. In the previous series on cybernetics, we looked at how to take the concepts of cybernetics, a sort of mid-century interdisciplinary field that combined early computer programming, physics, art, all sorts of things together, and how to use those principles to create interesting sounds on the modular synthesizer. Cybernetics grew at a time when analog computing was being used heavily, and the synthesizer, especially the Serge, is a type of analog computer. We first looked at how to create a neuron on the modular synthesizer following the perceptron model that was developed in the 1960s, and basically creating the fundamental building block of a larger artificially intelligent system on the synthesizer. We also folded in ideas on self-regulation from cybernetics, the idea that the cybernetic system observes itself and seeks to regulate itself whenever things move out of a certain bounds. In this series, we're going to dive a little deeper into the fundamentals of certain processes on the modular system. We're really going to explore the terms of linearity and nonlinearity, certain signal processors that either respond in a linear fashion or in a nonlinear fashion. On the Serge, there are a handful of circuits that respond either linearly or nonlinearly. The intention here is twofold. On the one hand is to understand these modules better, to understand what produces a linear response, what produces a nonlinear response, and how those things can be used together. And further, how we can use nonlinear dynamics and chaos in the synthesizer to model things like economic systems, weather patterns, and financial markets. On the other hand, our goal is more artistic, more abstract. It's to push a little further using the synthesizer and patch things in new and unexpected ways. To do things on the synthesizer that aren't readily obvious but can create interesting new sounds. I don't know what those sounds necessarily sound like right now, and that's kind of the whole goal. In this first episode of New Uses for Old Circuits, I'd like to talk about the Platonic ideal of Serge module, which is of course the dual slope generator. When people talk about synthesizers, you hear all sorts of things about East Coast versus West Coast, and Serge is always lumped in with the West Coast. That of course makes a lot of sense. Serge came out of San Francisco in the 70s, whereas the prototypical West Coast synthesizer, the Bula, came out in San Francisco in the mid-60s, about a decade earlier. And though they both use banana jacks and share a certain wackiness, there's a lot of differences between the two. For one, Serge has numerous famous filter designs, whereas Don Bula typically avoided using filters. More importantly, Bula's modules were very complex. Things like the 259 complex oscillator, the 296 spectral programmer, the MARF. These were huge instruments if you look under the panel, lots and lots of layers of circuit boards that combined a lot of different things together to create one musically focused instrument. By contrast, the Serge features really low-level circuits that you can reprogram and control. Things like the dual slope generator or the smooth and step generator are very simple slew generators, but they have lots of inputs and outputs and can be used to do a wide variety of things. Typically, they're used as control signals, things that make envelopes or modulation signals. But the other key difference between Bula and Serge is that in the Serge, audio and control is a very fluid concept, and nothing defines this better than the dual slope generator. In this instance, we're going to use the slope generator to process audio and to mimic the famous low-pass gate sound found in the Bula. The Bula low-pass gates used Vactrols to create a kind of amplifier that would also filter the signal as it closed down. That's to say that it controlled both the amplitude of a signal and the harmonic richness of that signal over time simultaneously. Let's start by plugging a square wave into the input of the slope generator and see what happens. As we adjust the rise, we start slewing the positive going part of the square wave. You can see that where the square wave goes from low to high, as we lower the rise time, it takes longer for that rise to happen rather than the immediate rise of the square wave. We get this smoothed out positive edge. The same thing happens with the fall. As we lower the fall time, it takes longer for the falling portion of the signal. It can't immediately jump from high to low. We instead smooth that out. And if we take it to extremes in either direction, we can completely defeat the incoming signal. Let's turn up the volume to hear that in action. You can probably already see where we're going with this. If we can completely silence the incoming signal by adjusting the rise and fall times, then, since we can modulate those rise and fall times, surely we can use the slope generator as a kind of voltage-controlled amplifier. The first thing we want to do is set the rise and fall time so that the signal is indeed completely defeated. So let's turn up the volume and just lower those in a symmetric way until we can't hear the signal anymore. Now let's start looping a second slope generator to make some envelopes and use those to control the rise and fall parameters. If we plug the output of this slope generator into the volt per octave input of the top slope generator, it's going to move both rise and fall simultaneously. And we get some enveloped sounds. The only problem with using the volt per octave input, however, is while it's really handy because we can only use one cable, it is calibrated for using the slope generator as an audio oscillator. It's calibrated to have a volt per octave response. We don't really care about that so much. We want to open the slope generator more than this jack will allow us because we don't care about the response being calibrated. We just want to have the widest range possible when opening and closing the slope generator. So we will instead take the output of the bottom slope generator and go to both the rise and fall independently. Now when we set it looping, you'll hear that we get a much wider response. The slope generator opens fully. You can see already that when the slope generator is fully open, we get our square wave, but it becomes more triangular as the slope generator, the top slope generator, closes down. The square wave with its sharp corners has a lot of harmonics, whereas the triangle wave is much closer to a sine wave and has a lot less harmonics. So what's really interesting is we can see the low-pass gate in action here, not only controlling the amplitude of the signal, but also filtering it over time, removing harmonics as the slope generator closes down. We can also change the symmetry of this response, leaving the rise time more open and having the slope generator only work on the fall time, or vice versa. Controlling the offsets for the rise and fall times, and also controlling the amount that the incoming envelope is skewing those things. This ability to asymmetrically filter your signal is a really interesting application of the slope generator. I can't think of any audio rate filter, as powerful as they may be, that gives you that much granular control over how you're filtering your signal. Because all the slew generator really is a low-pass filter. Sharp square waves in the audio domain become smooth triangles with the application of a low-pass filter. Just as sharp gates become smooth envelopes as we apply slew to them in the sub-audio range. But if you want a consistently symmetric slewing, we can instead use the smooth generator, which is part of the famous smooth step generator, the SSG, or in this case its updated version, the GTO. Let's take the square wave and go to the input of the smooth generator. Take our output, which is going both to the mixer output and to the oscilloscope from the output, and if we raise the rate, you can see we're getting our filtering, but you can see that just with one knob, we're always filtering the rise and fall, the positive and negative portions of the signal at the same time, symmetrically. So we get this nice square to triangle to finally fully silent motion. So now we only need one banana cable to go from our enveloping slope generator into the voltage control of the rise. So now when we start looping this, we'll get a classic low-pass gate. We can make the sound more percussive. We can reverse it. And in fact, we can even turn the rate up and invert the incoming voltage, do whatever we want. The slope generator and the dual slope generator and the smooth generator are both slew processors. The only difference is that the slope generator allows you to process the positive and negative going portions of the signal independently, whereas the smooth generator smooths out both sides at the same time. It's this very basic and simple process combined with lots of inputs and outputs that allows them to be so flexible. The slope generator and the SSG are also two of the key linear processors in the Serge system, but we'll talk all about linear and nonlinear processors in future videos.